Welcome, Calculus. This is section 8.8, Improper Integrals. The essential question is, what makes the integral improper? Let's begin. So the definition of a definite integral, you know this, and its limit as from a to b of f of x dx. The interval has to be finite. That's what we've done before. And also, the function f has to be continuous. We're actually going to now study a procedure where you can evaluate integrals that are not finite and are not always continuous. These types of intervals are called improper integrals. So let's talk about this a little bit more. Just remember that a function is said to have an infinite discontinuity from the left or right if it's approaching infinity or negative infinity. So for the example here, limit of f of x as x approaches c is approaching infinity. This could happen like if this was a c and your function is actually approaching an asymptote at c, just like this. Conversely, if you were going to negative infinity, and let's say that's your c right here, maybe your function's going down forever, and you have an asymptote at c. So those would have infinite discontinuities. Definition of improper integration, well, there's three ways to represent this. So what you're really looking for is your limits can be infinity. So infinity on the top, or maybe infinity or negative infinity, whatever on the bottom. And the way you think about this, instead of the integral actually being to infinity, just rewrite it as the limit of like b as approaches infinity, and put the b up there, and then just evaluate the integral. Same thing, it's down here in the a. Just the limit as a approaches infinity, and just integrate it for a. Now, if you have infinity or negative infinity on both of them, what we actually do is we split this up. So you pick a value for c, but maybe like c equals 0. So I'll write the integral from negative infinity to 0, and then from 0 to infinity, or c or 0 or some number like that. A little note here. We say that these integrals converge if the limit actually exists and actually is a number. When the limit diverges, there's no limit, and it's an infinite limit. It goes to infinity or maybe like negative infinity. Let's do some examples about that. So I want to evaluate this function right here. Integral from 1 to infinity of dx over x. So that's like 1 over x dx. Alright, so the first step I do is I rewrite this as the limit of b as b approaches infinity of 1 to b of dx over x. So let's integrate that first. The integral of 1 over x is going to be the natural log of x from 1 to b. And so that's going to equal the natural log of b minus the natural log of 1. And the natural log of 1 is 0, so it's just the natural log of b. But remember, now we have this limit as b approaches infinity. So what's that going to be? That's going to be natural log of infinity as you're going to infinity, and that ends up being infinity. So we say this diverges because it actually goes to infinity, which is diverging. And if you want to see a graph of that, here it is. So the shaded area starts at 1 and it keeps going to infinity. Notice it's getting smaller, but it doesn't actually approach a certain number, so we can say it diverges because it keeps getting bigger and it's not approaching a number. Alright, so infinite discontinuity. So a few other things, like it doesn't necessarily have to be limits at infinity or negative infinity. We can have discontinuities in the middle of the function. So a few ways this is represented. So if you have a function f of x and you're on an interval a to b and there's a discontinuity at b, then we can start doing limits as you approach b from like the left side, or you approach b from the right side because that's left side, or you're approaching a, the bottom limit, from the right side. So we just do one-sided limits for that. Also, if maybe you have a continuous function right here from a to b, except there's some hole in the middle or whatever asymptote, we just break those up from the integral to wherever that discontinuity is, from a to c to b to c. So that might look like a function like this. I could have a function like this, and then there's an asymptote going up like this, and maybe this happens when x equals, I don't know, 5. So I can break up that integral from, and maybe this was going from, I don't know, 0 to 10. But we have an asymptote right here. So I can say that's the integral from 0 to 5. So instead of the original being from 0 to 10 of that function f of x, I can say it's 0 to 5 of f of x plus 5 to 10 of f of x. And let's say I wanted to break that up more. So I'm going to follow the rules above here. Notice I have a discontinuity at 5. So like we said in point number 1, if you have discontinuity from the top, I'm going to rewrite this function as the limit of some value c approaching 5 from the left of the integral from 0 to c f of x. So this is basically doing this left side right here. And I want to break this one up, doing the same thing I do for number 2. It's approaching this asymptote right here. It's a 5, that's a 10. So I'm going to write this as the limit as c approaches 5 from the right of the integral from c to 10 f of x. I think you need to see some examples. So let's try one. I want to evaluate this one. So it's the integral of 1 over the cubed root of x. And here's a picture of this. So notice it's going from 0 to 1. 0, it never actually touches 0. It's an asymptote right here because you can't divide by 0. But how do we evaluate this? Well, since you can't plug in 0 to this function, I'm going to rewrite this as a limit. So it's the limit as, let's go, c approaches 0 from the right of the integral from c to 1 of 1 over the cubed root of x dx. So let's evaluate. That's the same thing as x to the negative 1/3 power. Integral from c to 1. I'm rewriting that dx. And so integrating this with power rule, it becomes x to the positive 2/3 times the reciprocal 3/2 from c to 1, which I'm going to rewrite as 3 times 1 to the 2/3 over 2 minus 3 times c to the 2/3 over 2. Cool. And remember, this is the limit as c is approaching 0. So the cool thing about this, we can evaluate this term right here. 3 times 1 to any power is just 3, so it's 3 over 2. This one, as you're approaching 0, you can actually just plug in the 0. And if it works, you're good. So it'll be minus 3 times 0 to the 2/3. But 0 to the 2/3, that actually works. That's just 0. So this whole term goes to 0. All right. So minus 0. So my answer is 3/2. So this, as you approach infinity, the area right here is 3/2. Let's try another one. Oh no, it's lagging on me. No, it's not. All right, pause the video. All right, let's try this out. So I want to evaluate this one. So I'm going to rewrite this as, I just want to cross out a few things. Let's do that. White. And I'm going to cross off this infinity and write this as b. So the limit as b approaches infinity of integral of e to the negative x. So the antiderivative is going to be negative e to the negative x from 0 to b, which is going to be negative e to the negative b minus negative e to the negative 0, which is negative e to the negative b plus 1. As b approaches infinity, you're going to get e to the negative infinity power plus 1. Negative infinity, this basically is just going to go to 0 plus 1, so your answer is 1. Now for the bottom part, again, I'm going to replace the infinity with something else. And I'm getting some lag. So I'm going to replace that infinity. I'm going to choose b again. Why not? And it's going to be b approaching infinity